So now let's talk about the basis of a subspace. Okay. So suppose we have H, and we know it's a subspace of Rn. So a basis for H is a set of vectors, call them B1 through Bp, in Rn that satisfy two properties. Okay. So one, they have to span H, okay? And two, they have to span H in an efficient way. That is, they have to be linearly independent. Okay, so if you can find a set of vectors that meets these two criteria, then they're a basis. Okay, so let's mention two useful facts here. Okay, the first one is that any set of n many linearly independent vectors in Rn are a basis for Rn. Okay? And so that follows from the invertible matrix theorem. Okay? So if you have n many linearly independent vectors in Rn, you can put them in a matrix A. Okay? That means they'll have linearly independent columns. Okay? And then from the invertible matrix theorem, that tells you that they span the set, and so we have a set that spans and is independent, therefore it's a basis. Okay. The second fact says that the columns of an invertible n by n matrix form a basis for Rn. Okay, and that this is also by the invertible matrix theorem. Okay. Okay, so let's talk about the standard basis. Okay, so the standard basis for Rn is the following set. Okay, so think about the identity matrix, right? It has ones along the diagonal. The columns of that matrix form a basis for Rn. Okay, so E1 is this vector, 1 in the first position, 0s elsewhere. E2 is this vector, 1 in the first vector, sorry, 1 in the second position, 0s elsewhere, and so on. Up to En, where it's 0s, all the way up to the nth position, which is a 1. Okay, so this is called the standard basis of Rn. Okay. Okay, and now we'll state the definition of dimension. Okay, so if we have a subspace H, the dimension of H, which we write as dim H, is the number of vectors in any basis of H. Okay, so for any H, there's always infinitely many possible choices for basis. Okay, but they're all going to have the same size. Okay, and that common number is called the dimension of the subspace. Okay. Okay, now I'll mention how you can tell what the dimension of a span of vectors is. Okay, so as we said, the span of a set of vectors is always a subspace. Okay, so suppose your vectors are v1 through vq. Okay, and our subspace is written here, the span of the vectors. Okay, so the dimension of the span is just going to equal the rank, where you're looking at the matrix with the columns set to the vectors. Okay, remember the rank detects the largest set of independent vectors among this set of vectors here. Okay, and that's going to tell you how big the span of these vectors is. So now let's talk about the basis theorem, which is very useful for identifying a basis for a subspace H, given that you know the dimension of H. Okay, so let H be a p-dimensional subspace of Rn. Okay. So any linearly independent set of exactly p elements is automatically going to be a basis of H. Okay. Also, any set of p elements that span H are automatically going to be a basis of H. Okay. So remember, what do we need from a basis? We need that it spans and that it's linearly independent. So from this theorem, it's saying that if you already know the size of the dimension of the subspace, and you know and you have p many elements in hand, you only need to check for one of these properties, because if it satisfies one of them, it automatically satisfies the other, and so it's a basis. Okay, so offers a bit of a shortcut there. Okay, if you can find p many independent sets, it's automatically a basis. If you can find p many vectors that span H, it's automatically basis. You don't need to check the other property. Okay, so here's a way you can sort of think about spanning sets and independent sets in H. Okay, so remember, for a p-dimensional subspace H, what do we want from our basis? Okay, we need it to be at least p many vectors to span H. Okay, so that makes sense. In order to span H, you're going to need at least p many vectors. We also need it to be independent, right? So independent sets in H have at most p many vectors. Okay, so we sort of demonstrated that before in Rn, where if we went above n many vectors, we said those are automatically dependent, right? So it's the same for subspaces as well. Okay, so in this drawing, or in this diagram here, if we let the sets that span H sort of be encompassed by this red circle, and the sets that the sets that are independent in H be encompassed by this blue circle, okay, where they intersect, okay, where the commonality is going to be the basis of H. Okay, so as you notice, it's easy to build up an arbitrarily huge spanning set, right? So if you have a set that spans, you can just keep on throwing in as many extra dependent vectors as you want, right? The challenge of a spanning set is to make it as small as possible. And with independent sets, the challenge is to make it as big as possible, right? Keep on adding in more vectors that are still independent, right? So where these two meet is where our basis for H lives. Okay, so let's talk about some subspaces that are associated to a matrix A. Okay, so we're going to assume the matrix A is an M by N matrix. Okay, so associated to A is the column space of a matrix. Okay, so we've mentioned this before. Column space of a matrix is the span of its columns. Okay, so if we write A where the V's are its columns, then the column space of A is the span of the columns. In other words, all linear combinations of the columns. Okay, and as we said before, the dimension of a span is the number, or is the largest number of independent vectors in it. So the dimension of the column space is the rank of A, right? That's what the rank identifies. Okay, so how do we find a basis for the column space? Okay. So we've also seen this. Okay, what we do is we compute an echelon form of A, and we identify the pivot positions in the echelon form, and then we go back to the original matrix and select the corresponding columns. That will give us a basis for the column space of A. Okay, so we've done that procedure already. Okay. There's also the row space associated to A. Okay, so the row space is what you think it is. Okay, it's the span of the rows of A. Okay, so if we write A where this is row 1, this is row 2, all the way down to row M, then row A, the row space of A, is the span of these R's. Okay, and the dimension of the row space is actually the same as the dimension of the column space, and it's determined by the rank of A. So how do we get a basis for the row space? Okay. What we do is we compute an echelon form, and then we select the non-zero rows of the echelon form. Okay, so for the row space, we're looking directly at the echelon form and picking out the rows that are non-zero. Okay, we don't go back to the original matrix. So you might ask why there's this difference between them. Okay. The answer is when you're doing row operations, it preserves the row space, but it ruins the column space. Okay, but the pivot positions are still good enough to highlight what we should be looking at in the original matrix of A to determine the basis of the column space. Okay. So now let's mention the null space. Okay. So we've seen this before. The null space of a matrix, okay, is the solution set to the homogeneous equation AX equals the zero vector. Okay. And the dimension of the null space is going to be n, the number of columns, subtract the rank. Okay. So we'll justify this in a bit, this formula here. So how do we find the basis for the null space? Okay, so what you do is you find the general solution for x for the homogeneous equation here, and you look at how it's parameterized, and from that you can see what the spanning set of the null space is. Okay, and we'll do an example that shows this off. Okay, so here's an example of a matrix A, and it wants us to compute the bases for the column space, the row space, and the null space. Okay, so it tells you that A is row equivalent to B. Okay, so row equivalent means that I can turn A into B by row operations. Okay? So since B is in reduced row echelon form, right, the problem is telling me that this is the reduced row echelon form of A. Okay? So how do we find the column space? Let's do that first. So the reduced row echelon form has pivots in columns 1 and columns 2. Right? That means we look back at the original matrix A, and column 1 and column 2 are going to be the basis for the column space of A. Okay? Now, for the row space, what do we have to do? We look at an echelon form, and we just take the non-zero rows. Okay? So this row and this row come directly from here. Those will be a basis for the row space. Okay? And you can see now that, or you can see why the rank of A, which is 2 in this case, gives you the dimension of both the column space and the row space, because each pivot identifies one column or one row that's going to go into the basis. Okay? And each basis adds a dimension. Okay, so what about the null space? Usually the null space is the most amount of work. Okay, so we want to solve for AX equals 0, the homogeneous equation. Okay, so I'm going to set up the augmented matrix A in the 0 vector. Okay, I know B is the reduced row echelon form of A, so the the reduced row echelon form of the augmented matrix is just going to be B in the 0 vector as well. Okay, so this is the setup here. Okay, so I have the same pivots, of course. Now I want to identify which of the 4 variables are basic variables and which are free variables. Okay, so column 1 and column 2 have pivots in them. They're basic variables. Column 3 and column 4 don't have any pivots. So they're going to be free variables. Now let's write out the general solution. Okay, so what does row 1 tell you? Okay, so what row 1 is telling you is that x1 plus 3x3 minus 2x4 is equal to 0. Okay, that's what row 1 is saying. Okay, so you just let the variables fall down to the coefficients, and the dotted line you can treat as an equal sign. Okay, and so when I rearrange, I can isolate for x1 like this. Right, just bring this over and bring that over, so that changes their signs. Okay, similarly for x2, I isolate for x2 and I get that it's equal to this. Okay, so now I can write my general solution. So right, the solution to AX equals 0 is going to be x, right? And then I like to write out the variables like this, okay? And then I fill in what I know about the variables. Okay, so I know that x1 is equal to this. I know that x2 is equal to this. And for x3 and x4, they're free variables. I just set them equal to themselves. Okay, and now I want to decompose this vector. Okay, so now we notice that x3s and x4s are the only variables left. Okay, so what I do is I write down x3, and then I write the coefficient from x3 from each entry here. Okay, so we have negative 3x3, 2x3, and 1x3, and none on the bottom. Same for x4. I have 2x4, negative 3x4, 0x4, and 1x4. Okay. So if you check, right, just multiply this out and then add it up, you'll get this back. Okay. So this is the generalized and parameterized form of the solution. Okay. And we remember that x3 and x4 are free variables, so they can be any number. Okay. So that means that this set is a span. Okay. We're taking linear combinations of these two vectors. Okay. They're independent vectors, so these are going to be the basis for the null space. Okay. So that's the procedure for finding the basis for the null space. And we'll need to remember how to do this when computing eigenvectors. Okay. Okay, now we're going to think a little bit more about the spaces, subspaces associated to the matrix A. So again, let A be an m by n matrix. So it has m many rows and n many columns. And at the beginning lecture, I mentioned this fact, that the columns of A can be thought of as vectors in Rm. Okay, so if you think about a column in A, how many entries does it have in it? Well, the number of entries it has in it is determined by the number of rows of the vector. So m many entries, so columns of A are in Rm. On the other hand, the rows are in Rn, right? Because if you're a row, how many entries do you have? You have n, determined by the number of columns. Okay, so there are actually two different spaces involved in A. Okay, so when you think about the action of A on a vector x, what size is that vector? It has to be an m by 1 vector, right? Because if you're multiplying A times x, these two numbers have to match, so x has to be a vector with n entries in it. Okay. And that means that ax has to be an m by 1 vector, right? Okay, so what's the implication here for our subspaces, the column space, the row space, and the null space? This means that the column space is a subspace of Rm, as we expected, and the row space and null space are subspaces of Rn. Okay, so these two subspaces live in different ambient spaces. Okay, so why is the null space in Rn? Well, because the null space is the solution to Ax equals 0, where the solutions are the x's that satisfy Ax equals 0. So Rn, so the null space is a subspace of Rn in that case. Okay, so we can visualize this in the following way. Okay, so we're going from Rn to Rm. That's the action of having a vector x in Rn and it being multiplied by A. Okay, so remember, matrix multiplication means taking linear combinations of the columns of A. So if we take linear combinations of the columns, which are in Rm, it's still in Rm. Okay, so in Rm over here, the column space lives. In Rn over here, the row space and the null space live. Okay, so all these spaces have to have the zero vector in it because they're subspaces. Okay, and how I've drawn them is just by a line. Okay, that's not usually accurate, right? The column space could be all of Rm, right? That would occur if A has rank M. It would be the whole thing here, right? It would span all of Rm. Okay, and again, I'm drawing the row space and the null space as sort of one-dimensional sets, but they could have varying sizes, right? Okay, so now I'll mention what's called the rank nullity theorem, which tells you the relationship between the sizes of these spaces. Okay, so this is the rank nullity theorem. Okay, so if we let A be an m by n matrix, okay, and we let the dimension of the null space, we're going to call it the nullity of A. So the nullity of A is just a number, and it's equal to the dimension of the null space. Okay, then we have this equation that n equals the rank of A plus the nullity of A. Okay, so what it's saying is that the number of columns, okay, equals the dimension of the column space and the row space plus the dimension of the null space. Okay, so this is interesting because it's like the matrix has n many dimensions to give out, and it's either going to give it to the column space or it's going to give it to the null space. You can think of it like that. Okay, and the proof of this is essentially by inspection of solving for these bases. So if we go back to the previous example, okay, so we had so our n is equal to 4, right? And when we computed the basis of the column space, we had 2 pivots, right? So that gave dimension 2 to the column space, okay? And then when we were computing the null space, the leftover columns, the columns without pivots, there's 2 of them, right? Each of them contributed 1 basis vector to the null space, right? So we see just by the echelon form that we have n many dimensions to distribute, and the pivots go to the rank, which correspond to the column space, and the non-pivots go to the nullity, which is the dimension of the null space. Finally, we'll talk about coordinates relative to a basis. Okay, so this is the definition. So suppose we have a basis B1 through BP, which is a basis for some subspace H. Okay? Now, suppose we have an X, another vector that just lives in H. Okay? We can write X as a linear combination of the basis vectors. Okay? Since the basis vectors span the set, there are some weights that allow us to write it as a linear combination of those basis elements. Okay? Now, these weights we can write as a vector on its own. Okay? And that's called the coordinate vector of x relative to b. Okay? So you have some x, and whenever we have just an x on its own, we consider it relative to the standard basis. Okay? So we have some regular x. We can write it in the language of this other basis by doing this. Okay? We can write it as a linear combination of this other basis and record its coordinates with respect to that basis. Okay, this is best seen with an example. Okay, so let's say the vector x is in a subspace H. Okay, and this is x over here, and we're given the basis for this subspace H to be B1, B2. Okay, so we have two basis elements, right? So this is going to be a two-dimensional space, subspace, inside of R3. Okay. How do we know it's R3? Well, the bases in X have 3 entries in them. Okay, so this is a plane through the origin in R3. Okay. So what we want to do is write X as a linear combination of the basis elements. Okay, so we want to figure out what weights we need to write this equation. Okay, and how we can do that is just by solving this equation here. Right, so we have a matrix. Think of this as A x equals B. Right? Okay, this time the x is the b, it's the known thing, and the unknown thing is the c's here. Okay, and we can solve such a system by writing the augmented matrix and then reducing. Okay, we write b1 here, b2, x, and we associate to the columns here the variables we're solving for. So we fill out the matrix, and we take the reduced row echelon form, and then we can read off what C1 and C2 should be, right? C1 needs to be 1/4, and C2 needs to be -5/4. Okay, so what is x relative to b? X relative to b is C1, C2, and we determine that it's these two numbers here. Okay. And we can double check this works by writing out the sum C1 times B1 plus C2 times B2, so these, and evaluating that, and we will indeed get x back. Okay, so you can ask some questions about this process, like, since this was just a two-dimensional plane in R3, what if x was outside of it? What if x was outside of that plane? Okay, here we're assuming it is inside of H, but what if it was outside of it? Well, what would happen is when we went to solve here, we would get no solutions. Okay? We would get 0, 0, and then a non-zero number here, which would decide no solutions to the system. okay, if our x was outside of H, which is possible, right? And we actually know this is going to be a unique solution, okay? So how do we know that? Well, we're putting in B1 and B2 here, and then we're reducing, okay? Since we know this is a basis, right? That means when we reduce it, each one of these will give us a pivot, right? Because they're independent, because they're a basis, okay? So since we get a pivot for each of our columns, we know that we'll never have infinitely many solutions, okay? We'll either get a unique solution when x is in the space, or we'll get no solutions if x is not in the space. Okay, now we'll look at and make an observation on a slightly different situation. Okay, so suppose that B is a basis for Rn. So we have n many vectors as a basis for Rn. Okay, and let's assume it's not the standard basis. Okay, it's some other basis. Okay. So let's assume x is in Rn. Now, if we wanted to write x as a coordinate vector with respect to b, here's what we can do. Okay, we can write P as the matrix with the vectors, the basis vectors as columns. Okay, and then what we want to solve is this equation. Okay, right, this is the unknown part here, and the x is known and the p is known. Okay, and to solve something like that, we write the augmented matrix with the matrix here and the known vector here together, and then we can reduce it and it'll tell us our answer. Okay, so what we did up here essentially. Okay, but in this case we can actually take another approach. Okay, so P is going to be an n by n invertible matrix. Okay, so why is it n by n? Well, there are n columns, right? And there are n rows because each of the vectors are in Rn. So P is a n by n matrix. It's invertible because its columns we know are a basis. Okay, and so bases are always linearly independent. So P has linearly independent columns, and by the invertible matrix theorem, that means P is invertible. And so P inverse exists. So if we're solving for this equation here, then there's another way we can solve for it. What we can do is multiply both sides by P inverse. Okay, so multiply on the left, I should specify, by P inverse. Okay, so P inverse appears here, P inverse appears here. We have P inverse times P, which is the identity. So this part just disappears. And so we get that x relative to b is equal to P inverse times x. Okay, so instead of reducing like this, we can compute the inverse of P and do matrix multiplication to solve for this. Okay, so we had a theorem earlier in the section about invertible matrices that told us we could do just this without having to go through the steps, right? We could solve this equation by directly just writing this. Okay, so let's think a moment about what this is saying in terms of bases and coordinates. Okay, so we're going to think about what these two equations are saying, this equation and this equation. So if we let B be some other basis for Rn, and we let P be the matrix as we defined it, okay, think about X in Rn. So X, which is in the language of the standard basis. Okay. If I multiply this X by the matrix P inverse on the left, it turns it in to X with respect to the coordinates B. Okay. So the action of multiplying by P inverse translates X into a B coordinate vector. Okay? And the other way around, if I have a vector that's a B coordinate vector, and I left multiply it by P, then it translates X with respect to B into X with respect to the standard basis. Okay, so the matrix P with columns as its with basis as its columns, and P inverse is sort of like a dictionary that allows you to go between these two sort of languages for Rn. Okay, so let's keep that observation in mind when we start talking about diagonalization in one of the next lectures.